video, we're going to go over the 2011 released FRQ number 2. So this is another chart problem. It says a pot of tea cools. The temperature of the tea is modeled by a differentiable function from 0 to 10, where T is measured in minutes and H is measured in degrees Celsius. Values of H as selected times the T are shown in the table. Alright. Use the data in the table to approximate the rate at which the T of temperature is changing at time 3.5. Okay. So we don't actually know the rate. We just know how hot it is at certain times. So at time 0, it's 66 degrees. At time 5, it's 52 degrees, and so on. It looks like it's decreasing the entire time. That makes sense because the T is cooling off. So at 3.5, we're going to use these values. There we go. That's going to go ahead and tell us the rate at 3.5. So we want to find H prime of 3.5. That's our goal here. So it's going to be 50, or H of 5 minus H of 2 divided by 5 minus 2. That's our average rate of change formula. So we have 52 minus 60 over 5 minus 2. And that's going to give me negative 8/3 degrees Celsius per minute. Cool. That's it. Part B. Part B says to, using the correct units, explain the meaning of 1/10 0 to 10 H of T and use the trapezoidal sum over 4 subintervals to find it. So the first thing I'm going to do is I'm going to go ahead and find it. So it's 1/10 the integral from 0 to 10 H of T dt. So it's 1 over 10. And the trapezoid equation is H over 2 B1 plus B2. So let me explain how to get H in all the values. So we have 4 subintervals. So that's going to be 1, 2, 3, and 4. And the way you get H is you do 2 minus 0. And then this is your B1 and this is your B2. And that's one trapezoid. To get the next trapezoid, it's going to be 5 minus 2. 60 is your B1 and 52 is your B2. And then that's how you get all your values. And you just kind of repeat that process. So in my trapezoid, it's going to be 2 over 2, 66 plus 60, plus 3 over 2, 60 plus 52, plus 4 over 2, 52 plus 44, plus 1/2, 44 plus 43. And you put that all in your fancy calculator and you get 1/10 times 529.5. Divide that by 10 and you get 52.95 degrees Celsius. So what this means is that 1/10 the integral 0 to 10 H of d dt is the average temperature in Celsius of the T between 0 and 10 minutes, or just during the first 10 minutes of it cooling. So then the average temperature is 52.95 degrees. And that makes sense if our top temperature is 66 and our bottom temperature is 43. The average should be somewhere in the middle, especially if it's just going down. Alright, so we're going to work out part C now. Evaluate the integral from 0 to 10 H prime of T dt. Using correct units, explain the meaning of the expression. So part C, it says the integral from 0 to 10 of H prime of T dt. Well, I know the antiderivative of the derivative is just the original. So it's H of 10 minus H of 0, which is going to be 43 minus 66, which is equal to negative 23. And so the integral from 0 to 10 of H prime of T dt is represents. Now, before I explain kind of just the answer, the derivative represents the rate of change of something, so it represents how much something has changed. So what this means is it's changed negative 23 degrees. So equals negative 23 means that the tea has cooled 23 degrees Celsius over the first 10 minutes. Alright, part D. At T equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. So right here, at T equals 0, you have 100 degrees Celsius. The temperature of the biscuits can be modeled by the differentiable function here. So this is the derivative, so this is the rate at which they cool. Using the given models, at T equals 10, how much cooler are the biscuits than the tea? So what I need to do is I need to figure out how cool the biscuits are at time 10. So to do that, I need to figure out how much they have cooled. So let me first write down some information that we know. We know at time 0, the biscuits are 100 degrees Celsius. Okay, so this is B of 0 right here. And I know that the biscuits cool at a rate of negative 13.84 E negative 0.137 T. Okay. So in order to figure out how much the biscuits have cooled, I'm going to go ahead and integrate that. So I integrate 0 to 10 B prime of T dt. And this is going to give me B of 10 minus B of 0. And my goal is to get B of 10. So I need to add over the B of 0 plus the integral of 0 to 10 B prime of T dt is going to give me the biscuits temperature at time 10. So B of 0 we know is 100 plus the integral from 0 to 10 B prime of T dt. And you put that all in your fancy calculator and you get 34.18275. So that means at time 10, after 10 minutes, your biscuits are about 34 degrees Celsius. So to find out how much cooler they are than the tea, you want to do H of 10 minus B of 10, and that's going to give you 8.817. So the biscuits are 8.817 degrees cooler than the tea.